So Tom really needs no introduction, yet I'm making my best attempt. So I thank Len for affording me distinct pleasure and honor to introducing Professor Thomas Marzetta to our distinguished lecture audience. So Tom is currently the director of NYU Wireless and a distinguished industry professor at NYU. He is also an IEEE fellow, Bell Labs fellow, and also a member of the National Academy of Engineering. Since his illustrious career is well captured by the printed bio, I just want to highlight two achievements that I can personally relate to and benefit from. So he is best known for originating the massive MIMO. It's a cornerstone technology that really made the MIMO multi-user spectrum efficiency gain scalable. And that actually made the 5G worldwide commercial success, largely in no small part, make that possible. And for this, he received the 2019 RCA Armstrong Medal, 2015 Stephen Rice Prize, and 2015 WRG Baker Award. So he's the lead author of the book Fundamentals of Massive MIMO. And since 2017-18 timeframe, he embarked on a physics-based wireless research agenda to approach performance limits that has evaded, I would say, by the overly simplistic communication theoretic models. So the cross-disciplinary approach resonates with me while I was still on the industry side and had led to inspiring interchanges to this day. He has since become a prolific contributor and advocate in this area, including creating a graduate course on the linear systems approach to wave propagation. This approach has yielded realistic radio propagation models, also bringing together fascinating new problems in signal processing, communication, and information theory, which some of them Tom would highlight today. Okay, so without much further ado, let's give a warm applause, round of applause for Tom.
Thank you, Xiaofeng. Thank you for the organizers of this event for inviting me, giving me the honor. This is a great turnout and marvelous facility. I wish we had an auditorium like this in Brooklyn. In any case, so the title of the talk is Impact of Classical Physics on Communication Theory. Why not quantum? Well, quantum's always been way over my head, and I believe that there's a huge amount of classical physics that we're not yet taking advantage of in our communication theory and in our wireless practice. So what I'll be doing in this talk is a half dozen or so very short sub-talks about various aspects of the activities of my group at NYU. So this goes way back, 20 years at Bell Labs. At the time, we had a director of research who reported directly to the president of Bell Labs. And one day, this director of research went to one of our big customers. It was either AT&T or Verizon, and came back with a real interesting question that the customer asked, which is, what does Bell Labs envision for wireless in the year 2020? I mean, just how often does somebody look, 17 years in the future, or is interested in the future 17 years ahead? So there was no ready answer to that prepared. So all of the wireless researchers at Bell Labs spent several months assembling an enormous 200-slide deck for the director of research. This was my slide. So on the left is a ancient warehouse in Ostia, which is the port city of Rome at the mouth of the Tiber River. And it's an amazing structure. You can go into it. But my thought was, well, what if you had an augmented reality helmet and very strong computing resources and very strong two-way wireless communication, so these computers could assemble for you in real time what the building would have looked like 2,000 years ago. And of course, maybe even put your comrades into togas or whatever was the fashionable dress at the time. All right, now, of course, augmented reality, we had just about a month ago the Brooklyn 6G Summit, and the big theme of that turned out to be something called the metaverse, which is basically augmented reality. The need for getting these incredible wireless rates, people project 2-3 gigabits per second, sustained throughput, both directions, no more than 10 millisecond latency. That's been what I've been pursuing ever since this time. Incidentally, my slide was dropped from the final deck. It was considered too futuristic? I don't know. So, as it is now, communication theory is really based on simplistic models, some would say overly simplistic. And maybe there's some echo here. Maybe get rid of that microphone. All right, I've been as guilty of that as anyone else. My book on massive MIMO, what does it do? Ignores interaction among antennas. The total power emitted by an array of transmit antennas is just the sum of the squares of the individual currents going into the antennas. The favorite stochastic model is called IID Rayleigh fading, which just means here I have, say, 5 transmit antennas, here 5 receive antennas. You have a frequency-dependent path between each pair of transmit and receive antennas. We assume that these are all random, Gaussian, and independent of one another, no matter how close the antennas are spaced. Very unrealistic. But you can do great things with this, not to say that this was a totally unproductive line of research. But now we want to make further progress. I mean, massive MIMO is a reality, as Xiaofeng said, in 5G. But I don't think it's up to the task of providing ubiquitous augmented reality service. For instance, if all of you were wearing an augmented reality helmet or going out into the green, I don't know of any wireless technology that could deliver the throughputs required. All right, so what do people think of? Well, some people are working on new forms of massive MIMO. So this cell-free massive MIMO, holographic massive MIMO, large intelligent surfaces, intelligent reflecting surfaces, and so on. My colleague Ted Rappaport believes in going to ever higher carrier frequencies. Thinks that the terahertz is the future. Who am I to dispute this? We need all of these approaches, but what I've been pushing for the last 5 years is to bring some more physics into the communication theory and the hope or expectation of breakthrough. So, when we say we need a closer union of physics and communication theory, well, what sort of physics are we talking about? Well, it can all be summarized quite simply. So every electrical engineer has studied Maxwell's equations at some time in her career. But where in the textbooks does it say that if I seat transmit antennas, receive antennas in a homogeneous medium, where does it say anywhere that this is, Maxwell's equations just describe a linear space-time invariant system? I've never seen that. But if this is so, and indeed it is, then actually the favorite tool of signal processors and communication theorists is just space-time Fourier transforms. Okay. Here's another principle which seems to be buried. A lot of people seem to know it, but where do you find it actually expressed? Which is, I take any system of antennas. I could have a transmit array here. I could have receive antennas elsewhere. The array could be distributed. The antennas could be arbitrarily close together. But if this is a linear and time-invariant environment, meaning nobody is moving around, there's no motion or anything, then guess what? This system of antennas is completely described by an impedance matrix. Just the knowledge of that fact means you can bring old-fashioned circuit theory to bear and actually tackle a lot of problems. You don't even have to know the numerical values of the entries of the impedance matrix. Just the fact that it exists is important. And the final thing is, if I have, let's suppose in this volume I have an arbitrarily complicated setup of antennas, transmit antennas. Once I'm clear of this, guess what? The external field can be represented exactly as a superposition of plane waves. And where do you see that? Again, a million people know it, but where do you see that in the textbooks? And this, of course, is just a generalization of the expansion of a spherical wave into plane waves. Very non-obvious, because we're all taught, everybody knows who works with arrays, beamforming, knows that if I have a spherical wave, if I'm sufficiently far away locally, it looks like a plane wave. But there's a much, much stronger and more exact statement, which is that everywhere I can represent this spherical wave as a superposition of plane waves. Very non-obvious and incredibly powerful. So that's what we're talking about here. Okay. So here are sort of 5 activities for my group. And I'll spend a few slides on each one. Wireless and resonant chambers, communication via conductive heat transfer, superdirective wireless power transfer, a Rayleigh-Jeans-Clark model for ambient thermal noise, and a new graduate course. So the first topic with my student Amrit Pal Singh, wireless communication in resonant chambers. So the idea is, let's turn the traditional paradigm of wireless engineering around. We passively accept some nasty propagation environment, and we have to cleverly try to design a wireless system that works rather well in that environment. But at least some of the time, we can turn that around and instead say, why not create the near-perfect propagation environment? If we can do that, why shouldn't we do it? Why make life more difficult for ourselves? So there is such a perfect environment. It's basically the interior of a copper box. So you could imagine this auditorium being made of solid copper, no windows, copper walls, copper ceiling, copper floor. Pretend that there's no metal anywhere else in the auditorium. So it's a perfectly reflecting surface. You transmit energy, it just bounces around. And it's a marvelous propagation environment. So what could we use this for? Well, potentially, you could have a robot-equipped factory, robots communicating without any wires and being powered without any wires. Because if this is a solid copper box, if I transmit 1 watt of power from this, it just bounces around, no attenuation. So anywhere I can put a receive antenna, pick up that 1 watt of power in theory, with 100% efficiency. Okay. These data centers that Google and Facebook run, tens of thousands of servers, humans never go in there except to repair things. You don't want anybody cluttering up the expensive equipment, so why not build it in a huge copper box, eliminate all the cables, and do all communication via wireless. Okay, these are long in the future, but this is sort of at the back of our mind as motivation. So what are some of the advantages? Well, you're completely isolated from the exterior environment. You don't have to worry about exterior interference. And moreover, you're not subject to rules and dictums of FCC. You can use whatever spectrum you wish and whatever power levels. That's nice. We talked about IID Rayleigh fading. Well, this copper box gives you as close to that as you'll find anywhere in the universe. Okay? It can't get any better. Just a 5-meter box at 3 gigahertz in a 10 megahertz band supports 10,000 modes. So if I'm deploying multiple antennas, it's not going to be the propagation environment that breaks down the system. There are always enough degrees of freedom to do what you want to do. And then finally, as I said, in theory, wireless power transfer is 100% efficient. So the physics of this is old stuff. The famous book by Morse and Feshbach, they give 3 solution techniques. Normal modes, so if I take a whiskey jug or something and blow across the top, as you know, you'll get a nice, pleasant, low-frequency note, and that's because you have acoustic modes inside of the, imagine this is like a box-shaped jug. The normal derivatives vanish on the surface of the box. That's the boundary condition. So they're basically sine waves and cosine waves that are flat at the ends. Okay, those are complete orthonormal set. You can get a complete solution that way. That's the Sturm-Liouville theorem. Much less obvious is there's a plane wave representation, and even less obvious method of images. Everybody has seen this. You have, say, a point acoustic source here. You have a planar interface that it bounces off of. How do you get the solution? Well, the simplest way is get rid of the barrier, pretend there is a fictitious point source on the other side, symmetrically opposite. The 2 sources emit identical waves. They meet at this planar interface. The normal derivative vanishes. That's the solution. That's called the method of images. Now this box, we can start to, we have a source inside the box. It's sending a wave out to the boundary, spherical wave. Well, we can sort of meet the boundary condition by putting an image outside. But when we put the image there, that causes trouble elsewhere. We have to put more images. It turns out that you need an infinite periodic array of images going out to infinity. And all of this stuff Morse and Feshbach do in 2 or 3 pages. This is sort of, it's interesting to point out that physicists don't make a big deal about mathematics. My experience with theoretical physicists is they always get the answer right, and the mathematics is never obvious, but they don't consider that important. Whereas if you look at electrical engineering publications, like information theory transactions, it's all mathematics. Okay. So there's plenty of theory for the communication theorist to draw on. Now, what we have here in this plot is we have a one-dimensional waveguide. You can think, this is acoustic version, but so you could think of it as an acoustic tube, like an organ pipe. You have a transmitter in it, you have a receiver, there's a transfer function as a function of frequency between the transmitter and receiver. And notice it's very violently behaving versus frequency. That's because of all of the resonances that take place. And interestingly enough now, if you try to make a communication problem out of this, so we allow the transmit source to have some power and some bandwidth within some spectrum. We assume a receiver with additive Gaussian noise, as we always assume. And we terminate the receiver effectively in a resistor. Now, how should we solve this problem to get the optimum capacity? Well, we should allocate the transmit power as a function of frequency. It's not a flat channel. It has these violent nulls and peaks. You do that, it turns out it sort of cancels out what's going on in the propagation, and you get an incredibly simple formula for capacity. The bandwidth, this is transmit power. This is a normalized version of the receiver resistance, noise spectral density, and bandwidth. And what's the peculiar thing about this? That is, I increase that receive resistor without limit, the capacity increases without limit. Very curious. And why is that possibly happening? Why do we think there's credibility to it? Because this is, because as the resistance gets bigger and bigger, there's no dissipative mechanism in the box. So if I'm transmitting it as constant power, the amplitude gets bigger and bigger and bigger. Hence, the SNR at the receiver gets bigger and bigger and bigger. Very, very non-obvious. Now, we've left some things out here, so our work is not totally complete. We're still working on it. I mean, if we have a resistor at the receiver, it itself is a source of Johnson noise that needs to be accounted for. And then there's the question of, does the box itself have any ambient thermal noise? That's a topic I'll talk about later, okay? So here are some research issues associated with this problem. Sensitivity of the channel to the details of the box. So people who actually have done experiments with these resonant chambers find the behavior, the channel between the transmitter and receiver inside the box is extraordinarily sensitive. You just touch the box itself or dent it in a little bit, it changes the solution violently, okay? So that's an interesting thing. Of course, actual resonant chambers have losses. How do we model that? Okay, the pure rectangular box is complicated enough. You're never going to get any analytical solutions of any sort for something more complicated, nor would you necessarily want to. Noise models I mentioned. Here's something. If this thing has no attenuation, then the delay spread is infinite. Can't use OFDM. We need to invent some totally new type of modulation. What it is, we don't know yet. Okay, and then finally, a related question. How much energy do we have to extract from a receive antenna to reliably receive 1 bit of information? Now, first of all, everybody has seen the old information theory formula. EB over N0 equals log 2. That's just a mathematical result. It has no physical validity of its own right. But there's a huge temptation to interpret EB as energy per bit extracted from an antenna in N0 as noise spectral density effectively at the input of your preamp. Totally unwarranted. So if you're going to ask this fundamental question, you can ask it at 2 levels. One is quantum mechanically. The other is according to classical statistical mechanics. And you're going to get different answers. And I say the more important one to focus on is classical statistical mechanics. Why? Because that's how we design wireless systems. You have this number noise figure, things like signal-to-noise ratio, white spectral density. There's no white noise in quantum mechanics. So I think you're going to get 2 different answers. With quantum mechanics, I'm prepared to accept the answer that you do probably need to pull some non-zero energy per bit out of an antenna. But the answer could be entirely different for classical statistical mechanics. And I hope to have the answer to that in a few months' time. Okay. Let's go to the next topic. Communication via conductive heat transfer. I'm very proud Ruth is a student of mine. We published a paper at the current GlobeCon conference, and it won one of the 15 Best Paper Awards. And so I'm hugely proud on 2 counts. First, that this research had nothing to do with massive MIMO. That's gratifying to move on to some other field and have some measure of success. Secondly, this is the first paper I've published with a student of mine. So very excited about this. So, conductive heat transfer. You think it's a very slow and sluggish process. You put your cast iron pan onto the stove for the bacon and eggs. You can put your hand in the pan for 15, 30 seconds, no discomfort. Very slow. But the heat equation is classified as a parabolic PDE, partial differential equation. What does this mean? It means that if I have a solution. So I have some source, distributed source as a function of space and time. It gives rise to a temperature solution. Okay. Now, if I shrink the spatial dimensions of the whole system by a factor of 2 in all 3 dimensions, then guess what? The solution speeds up by a factor of 4. So if I go from a scale of centimeters to microns, factor of 10 to the 4, then things go 10 to the 8 faster in time. So on a micron scale, maybe for application of wireless communication directly through silicon, maybe this could help out intra-chip communication. It seems a bit far-fetched, but it's, as you'll see, this is a fascinating research problem. There's a bit of a precedent for this. So everybody has heard of these horrific battles in the First World War, 105 years ago or so. And you would have these enormous shellings, sometimes 1 million shells in 24 hours. And so all communications between the front line and the reserve lines 5 miles back would be lost, because even telephone, telegraph cables buried 3 meters under the ground would still be torn apart by the shell fire. So both sides worked on what was called ground telegraphy. So it was found that if you put 2 iron stakes in the ground, say 1 kilometer apart, imagine that the trenches are parallel, and had just an old-fashioned electromagnetic buzzer with a telegraph key and a battery, it was found that at some parallel distance away, I could put another pair of iron stakes, or antennas, if you will, and with a sensitive receive circuit actually detect the current. So impervious to bombardment. And of course, this is the conductivity, the electrical conductivity equation is classified as an elliptical PDE. The interesting thing is, Howard Armstrong worked on that for United States. In Germany, Arnold Sommerfeld, everybody's heard of him, and I think 4 of his students got Nobel Prizes. And Richard Courant, the mathematician who wrote the famous book with Courant and Hilbert. Courant served in the German army in the First World War, was badly wounded and discharged from the army, and then worked on ground telegraphy. And in the 1930s, he had to leave the country, and he came and founded the Courant Institute for Applied Mathematics at NYU, which is still in existence. Okay, so there's a bit of precedent for this. But the heat equation is really qualitatively different from the wave equation, which underlies electromagnetic communications. So the impulse response sort of spreads out in space and time. So this is short time, longer time, longer time, longer time, and this is the impulse response as a function of space. So it just spreads out. That's, of course, consistent with our experience with heat conduction. Attenuates badly with frequency, exponentially. And the power constraint is odd. It isn't the same thing we're used to in most communications problems. So if SFT is the current feeding an electromagnetic antenna, then the power is proportional to the magnitude squared of the current, okay? If SFT is measured is the rate of heat flow into due to the source into the medium, joules per second, then if it's a thermodynamically lossy source, then the power is proportional to the magnitude. So anybody who knows something about information theory knows that this constraint has never been solved. Nobody knows the capacity for that. So we can, it's hard work. People just sort of worked on it, I think, as a toy problem. It isn't clear there was a real motivation for this, but we have a very good physical motivation for studying this problem. So so basically then, remember, we have a heat source, we have a receiver, maybe a thermocouple or a resistance thermometer type device, and there's a frequency-dependent channel between the two, okay? This channel, the frequency response decays very rapidly with frequency. So our allocation of transmit power is going to emphasize the low frequencies and de-emphasize the high frequencies. And in fact, if you do the classical water filling solution, at some point it isn't worth transmitting any more power at higher frequencies. You're just going to cut things off. So that's the qualitative nature. But another thing comes out of this, which is that unlike electromagnetic communications, bandwidth in thermal communication doesn't seem to be the same precious resource that it is in electromagnetics, just because of this very rapid attenuation of your channel with frequency. So some research issues. My student needs to learn more about the physics of transmitters and receivers. So if I have a resistance type source, which is just excited by electric current, that's thermodynamically lossy. Once I send power into the medium, I've lost it forever, the ability to convert the heat to, or the heat differential to mechanical work. If, however, I have something like a thermoelectric source, which you feed a current through, and one side of it gets hot and the other cold, that's at least in part reversible, which is to say, suppose I've driven it for positive heat, so I've injected positive heat into the formation. Now I want to go negative. Well, I can actually draw some power for a little while because of the temperature differential. So I haven't lost all of the power. So as you can see, we're going to get a fairly complicated power constraint from this. Okay. What about arrays, transmitters and receivers? MIMO activities needs to be looked at. Noise models, again, we can't use OFDM because this has virtually infinite delay spread. The final thing is an interesting thing, is the heat equation isn't consistent, the classical heat equation isn't consistent with special relativity. So if I suppose I have a steel I-beam lying on the stage, I light a match and touch at one end, the heat equation predicts instantaneously, 10 meters away, there is some rise in temperature, faster than the speed of light. Instantaneous. So it's been known for 100 years that this fails. So as we get to these very small scales, maybe this will kick in. We'll see. Okay, superdirective wireless power transfer. So the phenomenon of superdirectivity, though it wasn't called that at the time, was discovered by Sergei Shelkonov at Bell Labs in 1943. And but here is, everybody's heard of Jerry Foschini. He's really the father of point-to-point massive MIMO. My first day at Bell Labs in 1995, I met Jerry, and he told me his work on point-to-point MIMO, and I thought, by God, this is the greatest discovery of the century. This is going to make this company the most wealthy company in existence, and I want to try to invent something like this. Okay. But in the technical memo that he wrote with Mike Gans, there was a very interesting item in the appendix. The published version didn't have the appendix, but let's just read this. For example, consider a transmitting horn antenna with an aperture about 10 wavelengths on a side, located in outer space, roughly aimed at the Earth, with a 1 wavelength diameter supergain antenna on the Earth. It is possible to receive virtually all of the power radiated by the horn antenna. That's extraordinary. And this is not some quantum spooky action at a distance effect. This is classical electromagnetics, okay? So the question that's lingered for, 80 years, 85 years is, can we exploit this effect? It turns out people have on a very, very small scale. So my friend Bert Hochwald at Notre Dame worked at a West Coast WiMAX company, Basim, about 10 or 15 years ago on Wi-Fi handsets. And so in the handset, they used 2 very closely spaced dipole antennas, very close, so that deliberately there was strong mutual coupling among the 2 antennas. And in doing so, this gave each one a unique angular response. And so effectively, you were getting much greater angular resolution than a Rayleigh resolution limit would have predicted, okay? Rayleigh resolution limit simply says if I have an antenna aperture length L meters, then the narrowest beam I can put out is lambda over L radians, where lambda is the wavelength. That doesn't necessarily hold, okay? Superdirectivity supersedes that. Oh, I'm sorry. There we are, okay. So wireless power transfer, well, why are we looking at superdirectivity for power transfer and not wireless communications? A couple of things. When I was first trying to understand about 6 years ago superdirectivity, I thought I understood it well for a transmit superdirective array, but was having a great deal of trouble understanding how a receive superdirective array functioned. And so what I did was I thought, well, forget about communications. You got all these complicated noise models and other issues. But what if you're just trying to transmit power wirelessly? That's a very, in a sense, a simpler problem conceptually. And the other, so that's why I first started to look at wireless power transfer. Now, the other thing is, of course, nobody is ever going to, for communications purposes, resort to superdirective arrays without first doing much simpler measures, just going to wider bandwidth, for example, okay? So only after they've done that will they try to resort to superdirectivity. And so it seems a lot easier to work at a single frequency, which is fine for wireless power, than to try to work over a 10 or 20 megahertz bandwidth to make superdirectivity work. Okay, that's the reason. But other than that, of course, enormous payoffs if you can make wireless power work. Drones, operating rooms, factory robots. Okay, so let's try to learn a little bit more. Now, your first thought when you think of wireless power transfer is why not just take a microwave dish, aim it to the point, and transmit power? Well, I mean, people have thought of this for a better part for 80 years or more, and there have been some demos of this, but it's hopeless. Just a back-of-the-envelope calculation will tell you this. So we transmit, say, some transmit power in watts. We have a transmit antenna of area AT, so it gives a gain of AT over lambda squared, where lambda is the wavelength. And so at some range R, we get a power density. So this is where my drone is, say, 100 meters away in watts per square meter. We multiply by the aperture of the receive antenna, and that's the receive power. And we take the ratio of receive to transmit power, get this expression. We want that to be in the neighborhood of 1 or 1/2 or something. And so this says that the transmit aperture is given by this formula. So let's pretend we're trying to power a drone at an altitude just 100 meters away. That's not far. Let's suppose that the collection area on the drone is 10 centimeters by 10 centimeters, sort of like that. That seems reasonable for a small drone. Okay, and now this table says, let's look what happens at 3 gigahertz, 3300. Well, my transmit aperture at 3 gigahertz is 100 meters. In other words, the dish is as big across as is the range that I want to send the power to. Ridiculous. We go to 30 gigahertz, 10 meters, that's still a very large dish. Even 300 gigahertz, a 1 meter dish, is not insignificant. Forget about phased array technology. So if we space the antennas in the 2 dimensions in half wavelength, we still use 4 million elements in all 3 cases. So forget about traditional beamforming. It just isn't going to work. So it's got to be superdirectivity or not at all. So circuit theory lets you actually say some interesting things about wireless power transfer. So in general, I have a transmit array and I have a receive array. I'm trying to transmit. I transmit power from here, and I'm trying to collect power over here at the receiver, and I'd like to do it as efficiently as possible. Okay? Everything is described by this impedance matrix. So here we have, this is in partitioned form, so we have the vector of transmit currents, the vector of receive currents, the vector of transmit voltage, vector of receive voltages. That's all there is to it. Nothing more need be known. Populating this can be difficult, but it always exists, okay, even if it's difficult to compute. So with two interesting strategies, the optimum says we're going to jointly choose the transmit and receive current to maximize the power transfer efficiency. Okay, that's the best you can possibly do in terms of efficiency. Here's a greedy approach, which at first glance may seem to be just as good, but isn't. So suppose for a given transmit current, I sub nt, we choose this receive current to pull as much power out as possible. Now, the transmit array, while we're doing this, is then going to do a calculation, knowing that the receive array is pulling the maximum power out to maximize efficiency. You do that with this greedy strategy, you'll never do better than 50% efficient. And Tappan Sarkar showed this for single antenna case. Okay, this is very much analogous to, everybody has seen that if I have a voltage source with an internal impedance, if I want to pull maximum power out of that source, my load should have an impedance equal to the conjugate of the internal impedance, maximum power pull out. When you do that, however, half the power is just dissipated inside the source and half in the load, only 50% efficient. So the interesting thing is Thomas Edison pointed this out back in 1878. So the practice at the time was to build generators with the load matched to the internal resistance of the armature of the generator. Edison said, why should we do this? So he then built generators with internal resistance as low as possible, driving a much higher load resistance. There's a moral lesson in this, because the very best physicists of the day thoroughly knew Ohm's law and Joule's law. All the mathematics and physics was there, yet they really didn't understand what was going on. Okay? Let's think, so something philosophical to think about. Okay, the other thing, which may be obvious by reciprocity, so this is just the transpose of this by reciprocity, that sort of suggests that if I reverse the direction of power transmission, I should get the same optimum efficiency. And indeed, that's the case, but I haven't found an easy way to prove it, though we would be very surprised if it didn't happen just because of reciprocity. So superdirectivity. So here I have a linear array of antennas, and I'm trying, say, to send a signal or transmit power to a single receiver that's on the axis of this linear array. So this is called end-fire operation. Well, the idea of superdirectivity is the following. So it's known that if I have half wavelength spacing between these antennas, that my power gain of this array is just m, the number of antennas. So 10 antennas, a power gain of 10. If I put these antennas closer than a half wavelength, so there's inducing strong mutual coupling, it turns out that ultimately the gain is m squared. That's superdirectivity. Okay, and this was what Shelkonov showed. All right? So here I'm doing a toy calculation of transmitting power. I have 10 antennas here, and I'm trying to modest range of 5 wavelengths. So from the center of the array to this is 5 wavelengths. And just as an aside, when I do this superdirectivity calculation, it yields optimum currents to drive the antennas. But the numerical values of these currents grow without bounds as the spacing between the antennas gets smaller and smaller. You can right off the bat see that if there's any internal ohmic resistance in the antennas, at some point you're going to get unacceptable I²R losses. So we've accounted that for here by assuming some reciprocal Q factor, namely the ratio of the internal resistance to the radiation resistance is what we're specifying. And we go from 1 to 100 to 10 to the 4 to all the way to 10 to the 12. And so here it's a Q of 1. We start with a half wavelength, and we're just plotting the transfer efficiency. Nothing interesting happens. So go to 100. So again, the internal resistance is 1% of the radiation resistance on this brown curve. And notice what happens. There seems to be an optimum point at a little bit under 0.4 wavelengths. And our efficiency has increased by a factor of 2.5. And so by the time we have really a huge Q, we're getting a efficiency improvement, roughly a factor of 6, okay? Over conventional beamforming, so to speak. So this illustrates, you know, a little bit about what's going on here. I haven't explained the physics behind how it works, but you can ask me that later. But there's well-known problems with superdirectivity. So the impedance matrix becomes singular almost as the spacing gets shorter and shorter. And so at some point you have to invert that impedance matrix in order to compute the optimum powers. And if it's singular, it means that these the optimum currents. It means that the currents you're driving grow without bound. So that's a huge problem. Our real radiated power is under control, but we have enormous reactive power in the vicinity of the antennas. And what's wrong with that? Well, it means you have very high electric fields. Air can break down, arcing even. And of course, huge internal ohmic losses. And then finally, your solution has extreme sensitivity to all of the assumptions of the impedance matrix. So people have known this for years and years, and nobody's found a way so far to scale things up and get around these problems. What can we do? Well, superconducting antennas are a very obvious thing. Can metamaterials help? Maybe. New MIMO configurations? Maybe. This is what I call risky research, but we're willing to tackle it. Another problem, Rayleigh Jeans Clark. So Torkild Hansen works for a startup called Secneon. He was originally at the Air Force Cambridge labs. He's a recognized electromagnetic expert. Then he was at Schlumberger. I was at Schlumberger, but we didn't overlap. And then he found his own company for ground-penetrating radar applications and also RFIDs. But he and I have collaborated for a number of years. He's been teaching me further electromagnetic theory. I've been teaching him communication theory. So maybe you all remember the Rayleigh Jeans model. This was in the 1890s. Rayleigh and Jeans calculated what was the thermal noise in some radiating cavity. And they found that the spectrum went as omega squared, the square frequency. So this predicted that there, for a given finite temperature, that there was an infinite amount of thermal energy inside this cavity. Now, which of course is not so. The omega squared formula works very well up to about 10 or 20 terahertz, but then it starts to break down. And it was for this reason that Planck, of course, started quantum mechanics, was to fix the Rayleigh Jeans model. Clark was at Bell Labs, and he postulated a propagation model, which is like a 3D version of the Jakes model. The Jakes model, as you will recall, pretends that the propagation behaves as if you've got plane waves from all directions, random amplitudes, no preferred direction. Clark just is an extension of that to 3-dimension, okay? And so what our work does is it essentially melds these two theories. So we start out with a resonant chamber, And now, so if there's no external interference, then receiver noise, ambient thermal noise are the only possible impediments to communication in the box. So let's take a classical statistical mechanics approach. Again, remember you have these Sturm-Liouville modes, so these are cosines that are flat on the zero derivative on the boundaries. They constitute a complete orthonormal set. Now, classical statistical mechanics says that each one of these modes has a random thermal energy independent of the energy of the other modes, and that the expected energy is given by Boltzmann constant times absolute temperature over 2. So we consider these modes, we set them vibrating randomly with this expected energy, we sum them all up, and we get a space-time stochastic process for the pressure response, doing it acoustically, which is simpler than electromagnetically, inside the box. We let the box dimensions grow big compared with a wavelength, and guess what? We get a spatially, temporally stationary random field model for the thermal noise, the ambient thermal noise of the box. And so, so if we consider the spatial, so what this is the spatial autocorrelation as a function of temporal frequency. And so it's a function of the spatial separation, and this is just a spatial sinc function. This is what the Clark spectrum is. The temporal part in omega squared is the Rayleigh-Jeans formula, so we call this the RJC model. Okay, we're still trying to evaluate the implications of this for wireless communication inside the resonant chamber. All right. Finally, it's clear to do this sort of research, my students have to learn stochastic processes, communication theory, optimization theory, linear algebra, but they also have to understand the physics. And the best way to do that is to teach it to them myself. So if you're a double E, you learned electromagnetics the way a physicist learns it. So you have an E field, it's a function of space and time, magnetic field, space and time. You have some distributed electric current source, so any set of transmit antennas can be modeled this way. And you've got the 4 Maxwell's equations driven by this distributed electric current source. A physicist loves potential, so there's a scalar potential and a vector potential, and you remember, well, hard to remember, nobody remembers this unless you actually work with it, I don't remember it, but you express the E and H fields in terms of the potentials, and then it turns out that each of the potentials individually satisfies in a decoupled manner the wave equation. That's how they do it. They solve the wave equation by separation of variables. Physicists invariably love cylindrical and spherical coordinates, so you get all sorts of nasty Bessel functions and Hankel functions. It works great for the physicist. It solves all their problems, but I don't think this is the way the signal processor or the communication theorist should learn it. So how do I do it? Well, again, here are our Maxwell's equations. And again, you just look at them, and they obviously represent a linear space-time invariant system. Linearity, very easily shown. If I have this solution due to this source distribution, if I delay that source distribution in time and move it in space, guess what? My solutions for electric and magnetic field are delayed in time by the same amount and moved in space. So it's space-time invariant. So it means, guess what? That there is a convolution integral in space-time that takes me from the source distribution to the E and H field. So the source distribution is 3 by 1. The E and H together are 6 by 1. So this space-time impulse response, which of course in the trade is called a Green's function, same thing, is a 6 by 3 matrix. Well, if we have a convolution relation, then in frequency wave number, we have a multiplication. So there's this G matrix, again, is 6 by 3, but it's the temporal and spatial frequency response of the system. And so how do we get this? We take these Maxwell's equations and take space-time Fourier transforms of both sides. Okay? Once you do that, you solve a set of linear, and here they are in the frequency wave number space, the two, number 1 and number 2 equations. That's all we need here. And now we solve for 6 equations, 6 unknowns, and you get, guess what, an explicit solution for the electric and magnetic fields in terms of the source distribution in frequency wave number space. That's exact, no approximation, okay? All the wave equation action is in this denominator. And so if I work with a fixed temporal frequency and x and y spatial frequencies, then guess what? There's 2 poles in kz. So this thing is simple. This is a second-order differential equation in z. Any undergraduate should know how to solve that. That's what we always teach them, how to solve second-order ordinary linear constant coefficient differential equations. So you do that, you get these poles, you now take an inverse Fourier transform in kz, you pick up the residues. Anybody remember Cauchy residue theorem? And guess what? You get a plane in the exterior of the source distribution. So again, here's my source distribution. Now I'm talking about the field solution outside of that source. It's a superposition of plane waves that are parameterized by the temporal frequency and the 2 horizontal wave numbers. And so this is, of course, the extension of the Weyl integral for expanding the spherical wave. Okay, enough of this. So I've given you the flavor of this new course. Torkild, Hansen, and I are also working on a companion book by the same title. So conclusions. So we need a closer fusion of the physics and communication signal processing theory. Pretty clear that we have to educate our communication theorists and signal processors in a better way than we're now doing it. I think I know how to do that. Again, this philosophical point. We can have a complete mathematical and physics description of a phenomenon, and we still don't understand it. As I told you, Edison's discovery of how really to design a generator for efficiency. Okay, let me give you another example. So, 14 years ago, a group at MIT did an experiment which astonished a lot of people, and they actually published it in Annals of Physics, which is, of course, where Einstein published his most famous papers. It was very simple. This picture shows it all. This coil here, they drove with 10 megahertz. And over here is an exactly identical coil lighting up a light bulb. They claimed 40% efficiency. And notice the professor and students are all sitting happily in between, apparently unharmed by this. Okay? So I visited MIT shortly afterward on some other business and met with one of these gentlemen and congratulated him on having captured resonant evanescent coupling. That was the term they used in one of their publications. He laughed and said, well, you can explain 95% of the effect by old-fashioned electromagnetic induction. So when I got home, I just drew this circuit diagram. This is like an air core transformer, but the coupling coefficient is very poor. So the primary is driven by a current. It creates a time-varying magnetic field, but the secondary only picked up 0.2% of the magnetic flux. I mean, a high-quality iron power transformer, I think the secondary picks up at least 99% of the flux. But these guys were claiming 40% efficiency. Well, here's what happened. This is the actual formula you get for efficiency. This kappa is very small, but the Q's of these 2 coils were each on the order of 1,000, largely compensating for the low coupling coefficient and hence responsible for the 40% efficiency. Now, all of the mathematics and physics of a transformer was available for 100, 120 years. The mathematics and the physics were in place, but people still didn't understand it until this group came along. So that's a philosophical point to leave with you. I'm going to stop here. Thank you all. I've tried to say some provocative things, so I'll be very pleased to get some interesting or even pointed questions.
With a question, I have actually 15, but I was told to only ask one. So the idea of generating heat on purpose in silicon sort of gives me the willies, and because heat's kind of the dragon that we always fight. So I'm curious, ambient temperature and all these schemes, where does that play a role, and how does that, it seems like high directivity antennas would be particularly sensitive to that.
Yeah, that's a good question. We haven't looked at it yet, but it certainly would be a consideration in any sort of practical application of this heat transfer idea. Absolutely right.
Thank you. So the communication community and the engineers usually don't use physics, as you mentioned earlier in your talk, but that's because they can actually communicate without the need for understanding the physics behind it. However, as you also pointed out, there's a lot to be learned here. So how do we go and try to make this practice, which is already embedded into the systems, in a way to go back and maybe milk for more physics understanding? You know, the systems are built, and development of those systems doesn't require the knowledge of physics. Although I'm from the physics background and I enjoy the theoretical and practicality aspect of this, but in reality, how do you think that would force the community to go back and take a look at some of these physics problems?
Sure. A couple of aspects to your question. One is, it's definitely true, there's this gap between when actual practical wireless systems are developed. It seems you've got communication theorists who worry about OFDM modulation, signal processing, coding, error correction coding, computing, that sort of thing. Then you have the RF engineers who actually can design a patch antenna array and make the thing work, right, and power it up. And yeah, exactly. They work somewhat independently, and undoubtedly they get remarkable results. I mean, these beautiful 64-element massive MIMO arrays are an example of that. But the question is how to make further progress. And the fact is, we definitely are operating very far from any limits imposed by nature. So how can we approach these limits more closely? And over the years, all my experience indicates it's probably easier to teach communication theorists and signal processors wave propagation than to try to teach the RF engineers and electromagneticians communication theory. Though in the case of Torkild Hansen, I'm actually doing that to some extent. Okay? But the long-term question is, the only thing that's going to convince people really is if I and my group, and there are other people who are starting to take up this line of research, actually produce a breakthrough result that looks sufficiently promising that everybody says, gosh, we couldn't have done that. We just didn't know the electromagnetic theory and the communication theory. So that's what we hope will happen. Okay.
I have a question. So the linear time invariant system is assuming that the scattering environment is not okay. It's not time varying. So the extension to a more sort of real world, moving objects kind of environment, do you see any sort of hurdle in terms of?
It's a good question. We can do what we do now, which is we basically pretend that it's linear time invariant over an interval of time such that nobody or nothing moves more than, say, a quarter wavelength or a half wavelength. I mean, that's how we do that, right? And things work rather well when we work that way. So yeah, it is long term, it's time varying. Short term, though, it behaves as if it were time invariant. Now, of course, where that can break down electromagnetically some of the time, but we have underwater acoustics expert who will tell you that in underwater acoustics, you can have a delay spread this long in time, but actually the channel can change over a shorter interval than that. And what the hell are you going to do then? Then a time invariant well, good to start with because it's the one you can really understand, but obviously it's an enormous complication. Any amplification on that? I mean, fundamentally, a time-varying channel, if it varies on a short enough time scale, is not identifiable. It's a little bit like you have, somebody gives you a square matrix and says, you can transmit one vector, multiply this one vector by this matrix and look at the product. You can't identify the matrix from that one vector. And that's precisely analogous to the problem of sending a pilot signal through a truly time-varying system. It's not identifiable. So you either have to know the answer, or if there's enough structure to the problem, then you, of course, can predict, or if it's somehow sparse in some manner. But if it's just a general time-varying system, you're dead. You can't do anything that depends on knowledge of the channel.
So thank you. You had some wonderful, amazing, very fundamental pursuits of advances in wireless. Now, if you go back to that early part when you're talking about the Bell Labs projections of how things might look in the future for wireless
where
technology.
were we talking about back at the beginning?
You don't have to go to the slide, but your slide 1 really about the Bell Labs projections of the future of wireless.
An old favorite of mine. There we are.
Yeah. So if you look at the approaches you're using on the fundamental wireless technologies, do you have any particular applications that you could envision that are going to be truly transformative based on some of these things like thermal transport or?
Well, for this problem, I think you're talking about superdirectivity, and you're talking about making it work on a very wide bandwidth, and so that's very ambitious. I mean, could the curators at Ostia, it's a great place to visit, by the way. I was there back in 1983 with my wife. We had the whole place to ourselves and could crawl under temples and so on. But you know, conceivably they could put some sort of network hidden in various places that might provide enough coverage so people could actually wear an augmented reality helmet. But think of the computation that would be required. You know, you want to capture everything that you're seeing without the helmet, but superimpose on it the result of all these incredible calculations. I think that you need very strong computing, and it has to be, of course, can't be too far away because don't people get motion sick if the delay is more than 10 milliseconds? Yeah.
So there are other, like, more transformative, very different paradigms, let's say.
Yeah.
Such as, like, here you're looking at somewhat conventional, like, high bandwidth, you know, high speed communications. If you look at, say, very dense IoT networks, for example, that couldn't otherwise be achieved with today's wireless technology.
Yeah. Not sure I have a really satisfactory answer.
All right.
Maybe someone else has some comments on that? Or?
Great questions. I think some of the questions could follow up in the reception period. So thank you again, Tom, for
Well, thank you, folks.
Wonderful.